Now that we know how to handle derivatives when calculating a Laplace transform, and we know how to calculate an inverse Laplace transform, let's actually solve some differential equations. So let's start with this one. So y prime minus 7y equals e to the minus 3t, and we have this initial condition, y of 0 is 4. Notice that this actually is a first order equation. It's first order linear. We could solve this using the techniques that we already developed that don't involve Laplace transforms, but it's nice to see that the Laplace transform can handle even these earlier cases. So let's take Laplace transform on both sides, and I'm going to immediately use the linearity of the Laplace transform when I'm writing down the left-hand side. So we get Laplace transform of y prime minus 7 times Laplace transform of y equals Laplace transform of e to the minus 3t. So Laplace transform of y is s times Laplace transform of y prime is s times Laplace transform of y minus y of 0 minus 7 times Laplace transform of y equals, and then Laplace transform of e to the minus 3t. This is one that we have a rule for, right? We already calculated the Laplace transform of exponentials like this, and what we got was 1 over s plus 3, right? Remember, in general, the Laplace transform of e to the at is 1 over s minus a. Since our a value is negative, it's negative 3, the minus sign in the middle here turns into a plus right there. Okay, so now we can gather up the Laplace transform terms. We get s minus 7 times the Laplace transform of y. Okay, this y of 0 right here is 4. And since that doesn't have a Laplace transform of y in it, we're going to move it to the other side. So the right-hand side is 1 over s plus 3 plus 4. Now we can divide both sides by s minus 7 to finish solving algebraically for the Laplace transform of y. We get 1 over s plus 3 times s minus 7 plus 4 over s minus 7. All right, now that we have solved for the Laplace transform of y, we need to do the inverse Laplace transform. So on the left-hand side, we just get y. On the right-hand side, we're going to need to do some partial fractions here. So for now, I'll just write inverse Laplace transform of 1 over s plus 3 times s minus 7 plus 4 times inverse transform of 1 over s minus 7. Okay. Now this rational function in our first inverse transform, since its denominator is a product of linear factors, we can use the cover-up trick to figure out what the numerators should be. So for covering up covering up s plus 3, plug in minus 3 for s, and we get minus 10. And then covering up s minus 7 and plugging in plus 7, you get plus 10. Sorry, these should both be 1 over those. Okay, and then s minus 7 down here. And this inverse transform, the final one here, we might as well work out right away. So it's 4 times inverse transform of 1 over s minus 7 is e to the 7t. Okay, so now we need this minus 1 over 10. That's a constant multiple, so we can move that outside of this inverse transform. So minus 1 over 10 times inverse transform of 1 over s plus 3 plus 1 over 10 times inverse transform of 1 over s minus 7, and plus the part we already worked out, 4e to the 7t. All right, so minus 1 over 10. Inverse transform of 1 over s plus 3 is e to the minus 3t, plus 1 over 10 times inverse transform of 1 over s minus 7 is e to the 7t, plus 4e to the 7t. And we might as well combine those last two terms. So our solution is minus 1 over 10 e to the minus 3t plus, looks like 41 tenths times e to the 7t. So you can see this process of using the Laplace transform to solve a first order example actually wasn't bad. So maybe there's maybe a little more algebra than it would be using our older techniques for solving a first order linear equation, but there was less calculus. So I don't know which way is better. It's sort of up to you, but it's nice to see at the very least that the Laplace transform can handle this kind of equation. All right, let's look at one more example. How about this one? Y double prime minus y equals e to the minus t, and then we have some initial conditions here. So we're going to take Laplace transform on both sides. So we get Laplace transform of y double prime minus Laplace transform of y equals Laplace transform of e to the minus t. All right. Now Laplace transform of y double prime, we have a formula for that. That's s squared Laplace transform of y minus, then the power of s goes down by 1 and the derivative on y goes up by 1. So s times y of 0, and then again the power of s goes down to 0 and the derivative on y goes up 1, so y prime of 0. Okay, and then minus our Laplace transform of y. On the right hand side, Laplace transform of e to the minus t, that's one that we know, that's 1 over s plus 1. Now we might as well put in our initial conditions here. So since y of 0 is 0, this middle term goes away. And since y prime of 0 is 1, this y prime of 0 term is just 1. Now gathering up all of our Laplace transforms, we get s squared plus 1 times the Laplace transform of y. And then moving this minus 1 to the right-hand side, we get 1 over s plus 1 plus 1. All right, now we need to solve this equation algebraically for Laplace transform of y. We get Laplace transform of y equals 1 over s plus 1 times s squared plus 1 plus 1 over s squared plus 1. Okay, as usual, to take an inverse Laplace transform, we're going to have to work out the partial fractions decomposition of this first term on the right-hand side. So let's just do that now. So let's set this equation to the side for a moment and work out this partial fractions decomposition. I'll sort of do it maybe a little faster than usual. So let's see, we're going to get, when we write down the partial fractions term and then clear the denominators, we're going to get something like 1 equals s squared plus 1 times a plus bs plus c times s plus 1. If we plug in minus 1 for s, we get 1 equals 2a. So a is a half. And then, let's see, what should we do? Well, let's multiply everything out, I guess. 1 equals, a is a half, so we get 1 half s squared plus 1 half plus bs squared plus cs plus bs plus c. Okay, so on the right-hand side, we have, for our s squareds, we have b plus a half. For our s term, we have b plus c. And for our constant term, we have 1/2 plus c. Okay, now comparing coefficients, we know the s squared term has to be 0 because there is no s squared on the left. So 0 equals b plus a half, so b has to be minus a half. Looking at the constant terms, 1 has to equal 1/2 plus c, so c is a half. And then it had better be the case that b plus c equals 0 because there is no s on the left-hand side, but b plus c is 0, right? There's no coincidence here. It had to be this way. If we came up with, by equating coefficients, if we came up with equations that were inconsistent, that would be an indication that we made an algebra mistake somewhere. Okay, at any rate, so we found the Laplace transform of y, and it was, so this first piece is a over s plus 1, so 1/2 times 1 over s plus 1, plus bs plus c over s squared plus 1. b is minus a half times s plus c is plus a half. Okay, now we can take the inverse Laplace transform. On the left, we just get y. And then on the right, 1/2 times the inverse transform of 1 over s plus 1 plus, and then again, I'm going to split up the numerator here so we have one piece with just s in the numerator and one piece with just a constant in the numerator. And also, when I write down the Laplace transform, I'm going to move these constant multiples outside of the inverse transform. So I guess I need a minus 1/2 times the inverse transform of s over s squared plus 1 plus 1/2 times the inverse transform of 1 over s squared plus 1. And so we finally get, as our solution, y is 1/2 times inverse transform of 1 over s plus 1 is e to the minus t, minus 1/2 times inverse transform of s over s squared plus 1 is cosine t, plus 1/2 times this last term gives us sine t. All right, and we're done. That's all there is to it. Notice that one nice thing about this is it's not at all uncommon for initial values in applications to be 0. And when you have an initial value that's 0, like here, notice it always knocks out a bunch of terms that might have shown up. So having initial values that are 0 makes this a lot easier to, makes the resulting inverse transform a lot easier to calculate. This is as opposed to, if we were going to solve this sort of equation using undetermined coefficients, sort of the quote-unquote traditional way to do it, we wouldn't get to use our initial values until much later in the process, and so we would have to carry around all of these unknown constants for a lot longer, which would make the algebra a lot messier. So it's nice to be able to use these initial values early in the process instead of late.